Hello, everyone. Thanks for coming. My name is Abdel Rahman. I'm an incoming graduate student at the University of Washington. And I took part in this research as part of my fellowship at IRIS-HEP, which is the Institute for Research and Innovation in Software for High Energy Physics. And basically what it is it's like a feasibility study. We want to see if we can actually implement graph neural networks as triggers at the high luminosity LHC. And so what's it all about? So we have this overarching problem is that because of the expected increase in pile up during the high luminosity phase, we're going to need faster, more efficient particle tracking algorithms. And so researchers have discovered that graph neural networks are well suited to this particle tracking task, or at least part of it, which I'll explain in a second. And so that's the machine learning problems. What are graphs? What are graph neural networks? How can we use them for particle tracking? How well suited are they to the task? And then the hardware problem is, how do we implement these GNNs on actual electronics at the LHC? And how do we make sure that they're fast enough for the trigger system? And so the short answer is that we implement them on these type of semiconductors called field programmable gate arrays, or FPGAs for short. Sorry, FPGAs. So we're going to talk about FPGAs. We're also going to talk about high-level synthesis, or HLS for short, which is the language we use to kind of program FPGAs. And then also I'm going to go over our efforts to implement these high-level synthesis, particle tracking GNNs, and whether we found that they're feasible for use at the high luminosity LHC, given the latency and the timing restrictions. So start with the overarching problem. How fast do we need to perform particle tracking? At the CMS detector, the level 1 trigger, which is kind of like the first level trigger, has a strict 4 microsecond latency limit. So once a collision event happens, we want it out the other end of the level 1 trigger within 4 microseconds. And because this is a pretty low trigger, pretty low limit, we usually implement the L1 trigger on FPGAs, those semiconductors I mentioned earlier. But there's also the high level trigger, which we can implement on CPUs sometimes because it has a more modest output rate of 1 kilohertz. So current particle tracking algorithms scale worse than quadratically with the number of detector hits. So like each time a particle goes through one of these layers. And the high luminosity phase is expected to increase the number of proton-proton collisions by a factor of between 5 to 7. So there's going to be a lot more detector hits. And that's why we need faster particle tracking algorithms. And that's where graph neural networks come. So how do we use graph neural networks for particle tracking? Well, they're really good at one part of the particle tracking pipeline, which is track segment construction. It's basically finding adjacent pairs of adjacent detector hits, which were both caused by the same particle. And so basically a graph neural network is a neural network that works with graph structured data. And you can think of it as a graph to graph mapping. Its input is a graph, right? It's a set of nodes and a set of edges and some definition of, which nodes are connected by which edges. And in return, the GNN will also return a graph. It can return a set of nodes and or a set of edges and or some connectivity definition. And so because neural networks in general are really good at least, regression and classification, GNNs are pretty good at node regression, node classification, edge regression, and edge classification. So if a GNN were trying to predict the features of like one or several of these nodes, that would be node regression. If it were trying to, bin these nodes into different classes, that would be node classification. And the reason these GNNs are so good at track segment reconstruction is because that's basically an edge classification task. So how does this work? Well, we start with this pre-processed data, right? So we've taken the raw data, which is basically a point cloud of detector hits, and we've embedded each detector hit as a node in our graph. And if we connect all the nodes, right, connect each node to every other node, that gives you a set of edges as well. And a set of nodes and a set of edges, we have a graph. This is our graph structured input. And these black edges over here at the start we call these track segment candidates, because each edge might possibly indicate that the two detector hits it connects were caused by the same particle, but we don't know for sure yet. So we call it a candidate. Now, what we work with this GNN called an interaction network, and what this interaction network can do is, if it's trained properly, it can tell you which of these edges actually do, in fact, connect, a pair of adjacent detector hits that were caused by the same particle. In other words, it's telling you which of these edges are true edges and which of these edges are false edges. So it turns out that the track segment reconstruction task is naturally embedded as an edge classification task. And so that's what makes them so well suited for the track segment reconstruction. But there's a bit more to the whole particle tracking workflow. So the interaction network does this edge classification part, but we start right from here with the raw detector data, which is basically a point cloud of detector hits. And then we construct it into a graph using a little bit of cleverness. And then our interaction network returns a true set of track segments. Ideally, then you would connect these track segments into sequences of track segments, where each sequence presumably defines one entire particle track. There is past and ongoing research to perform this full track reconstruction phase, but for now we're going to focus on just part A and part B. Part B is what the interaction networks are really good at. So how do we, what data do we use? We use the TrackML data set, which I noticed was mentioned in the last presentation. So basically, this is a simulated data set of collision events based on like the pile of conditions expected at the high luminosity phase. And there's a link for it right there. So this data set is basically a point cloud of detector hits, and we want to convert this into a graph format. And earlier, I gave a bit of a simplified explanation for how this happens. Simplified explanation. So I said that we just connect every edge with every node with every other node to get our edges. But it turns out that's not the most efficient way to do things. We don't need to consider every possible pair of detector hits as a possible edge. So if we use a bit of cleverness, we can get a better set of candidate track segments. And that's what this graph construction part is for. So we can start with certain exclusions on edges that we want to consider. For example, we can set a maximum value of the phi slope. Now, without getting too technical, this phi slope is basically a linear approximation of like the track's curvature. So as you decrease this value, you'll get graphs that show more and more, or less and less curvature, or particles with more momentum. And then we can also set a maximum value of Z0, which is basically, how far from the center of the collision a track started. We can also set limits on which nodes we want to consider. So for this research, we don't consider nodes with a detector hit energy of less than 2 GeV. So 1 GeV hits are excluded. And we can also perform segmentation, which is where we take the 3D volume of the detector and split it into different slices and consider each slice on its own as its own separate graph. Because we can mostly expect that particles will travel radially from the center of the collision. If we base this the segmentation just based on the angles phi and eta, like the radial and azimuthal angles, we don't lose too many track segments if we perform the segmentation. But just to check, we ran some numbers to see what kind of a trade-off there is. So the efficiency we defined as the number of true track segments that made it through the segmentation cut over the number of total true track segments that existed before the segmentation cut. And the purity is the number of true track segments that survived the segmentation cut divided by the number of total track segment candidates that survived the segmentation. And so you can see there's a bit of a trade-off between efficiency and purity. We chose 8 eta sectors and 2 eta sectors and 8 phi sectors, which gives us 98% efficiency, 57% purity. But this low purity is basically the problem that the interaction network is intended to solve. It's supposed to discriminate between the true and the false track segment candidates. But what do we get in return for this segmentation? Well, our parameters, we end up with 113 nodes and 196 edges as like the 95th percentile of graphs are, have that many nodes and edges. And you can see if we were to perform no segmentation at all, that would be 1,400 nodes, about 3,000 edges. And remember, current tracking algorithms scale worse than quadratically with the number of detector hits, i.e. nodes. So this saves us a good amount of time and resources. So this is the actual graph neural network that we use. These edge blocks and node blocks are each an MLP, like a multi-layer perceptron. This aggregation block is not. So this aggregation block, what it does is it combines, well, let me start from the top. This edge block performs what we call an edge update. It takes the current value of each edge and the value of its sender node and its receiver node, and it uses that to compute a latent implicit edge feature. We sometimes call this a message. And then this aggregation block, for each node, it takes all of the incoming messages that were just computed, or the incoming latent edge features, and it uses that along with the current node features to perform a node update. So the aggregation block gets the aggregate of all these messages, and then the node block performs the node update. And then this final edge block performs another edge update, but it has a sigmoid activation. So it ranges between 0 and 1. So the way we interpret the output of this edge block is it's computing the probability of each edge being a true or a false track segment. Yeah. And so how do we actually implement these on electronics? Well, if you were to try to store a normal PyTorch neural network on like some system RAM and use it as a trigger, right, on some normal CPU or GPU, you'd probably exceed the 4 microsecond L1 latency limit. So what we're doing is we're using FPGAs, which are several layers of abstraction below a normal programming language like Python. So Python's up here. FPGA, earlier I said they're programmed, but really you can think of it as a reconfigurable electronic circuit. So if you have an electronic circuit made up of logic gates like NANDs and ANDs and either ors, basically an FPGA is full of tiny logic gates, which you can reprogram on a computer. But the more accurate term is design. You design it. And because they're at such a low level of abstraction, they can be very fast for certain applications, but it also makes something like designing an entire neural network impractically time-consuming and expensive. So we get around this with this tool called HLS for ML, which stands for high-level synthesis for machine learning. So FPGAs are down here. They're designed in hardware description languages, but Xilinx, which manufactures FPGAs, has support for something called high-level synthesis, right, HLS, which is at about the same level of abstraction as C. In fact, it's very similar to C, but still, you don't see many neural networks being designed from scratch in C, and that's what this tool does. This tool basically allows us to take Python neural networks trained in PyTorch or Keras or Onyx and convert them into high-level synthesis design, which Xilinx can then decode into a hardware description language, and then you can throw it on an FPGA. So for this project, we expanded the functionality of this HLS for ML tool to work with a specific PyTorch add-on called PyTorch Geometric, right? That's the PyG part, and PyG to HLS. So we train these graph neural networks in PyTorch Geometric, use this HLS for ML tool to convert them into high-level synthesis and FPGA projects. And so now we can kind of look at the big picture a little bit. The machine learning part, we start with this raw detector data, use some clever graph construction to get it into efficient, to get a set of smart track segment candidates, use the interaction network to classify these into true and false track segments, and ideally you would then go on to connect the track segments into full tracks. And for the hardware workflow, we're starting with Python neural networks, using this handy tool to convert them into high-level synthesis designs. So before we can look at the results, I have to mention two quick things. So basically, when we convert a neural network from Python into an FPGA project, we can choose to decrease the number of bits of precision we're using to represent the neural network. So whereas a neural network in Python is typically represented in 16, 32, or 64 bits, we throw it on an FPGA because we do want to save resources and time. Resources, I mean, as in like actual hardware resources on the chip. We can often represent it in fewer than 16 bits. And when we reduce the bit precision, we call this quantization. So there's two ways to quantize the model. We can do post-training quantization, in which we train the model in the full floating point precision and then quantize it to 16 bits. Or we can do quantization aware training, where we first quantize the model and then train it. So during quantization aware training, while you're actually performing stochastic gradient descent and looking for this, hyperdimensional minimum, you're doing this in already reduced precision. And some research has found that quantization aware training can increase your model performance if you're going to quantize it anyway. And one more thing. So FPGAs, because they're kind of electronic circuits and not a literal computer program, they don't have dynamic memory reallocation. So they expect like static fixed size arrays for any array that they do accept. And this poses a problem for graphs because graphs can have, a variable number of nodes and edges. So to get around this, we pad or we truncate all our input graphs before feeding them to the high level synthesis, model, the HLS model. And so what does this mean for the actual performance of it? In terms of padding, right, if the actual graph is too small and we're just adding some dummy nodes and edges, this is usually fine. With the exception of a few very specific instances, you can usually construct a dummy graph that's completely disconnected from the actual graph. And so there's no information lost or shared between the two, and you get exactly the same output that you would if you were just acting on this actual graph. In the case of truncation, however, there's really no way to get around the loss of information from excluding certain nodes or edges from consideration. So this will have an effect on the performance. However, basically the fixed size that the HLS model expects is dependent on how many actual resources you have on your FPGA. So as you get to larger and larger FPGAs that expect a larger and larger fixed size, you can eventually eliminate the need for truncation in the first place. So this is something that you can just throw some money at, it seems. And so now we can look at the actual precision or the performance of these HLS GNNs. And there's a lot going on here. So this y-axis is AUC, it means area under the curve. It's the area under the receiver operating characteristic curve. It's not exactly the same thing as accuracy, but it basically means like how well the model performs this track segment construction task. On the x-axis, we have how many bits we're using to represent the model. So remember, when I mentioned quantization, so from 0 to 18 bits. And these dashed lines are the model's performance on non-truncated, non-padded graphs, so like the actual raw graphs as they are in the TrackML data set. The solid lines is, show the model performance on truncated or padded graphs. The blue lines show the model's performance using post-training quantization, where we train it and then quantize it. And the orange shows the model's performance if we quantize it first and then train it. So that would be, quantization aware training. And basically, we can reproduce the full 64-bit, floating point precision model's performance at about 10 or 12 total bits, which is pretty good. And you can see that the effect of this, graph padding or graph truncation is about 5%. And that's for, of course, nodes that are, I forgot to mention, nodes that are padded or truncated to 113 nodes and 196 edges. Now for all of these, all right. So we settled on two main implementations. Sorry. There's the throughput optimized backend. So these two implementations are different hardware versions, hardware translations of the same exact interaction node. So there's basically two ways to do it. But the point to remember is that they're logically the same. They have the same exact output and they're translations of the same exact Python object on the front. The throughput optimized version is supposed to be faster, but uses more resources and scales to smaller graphs just because the HLS compiler can only scale to a certain size for this design. And the resource optimized implementation uses less resources, but it's a little bit slower and it scales to larger graphs. So this is the precision scan for the throughput optimized model. So we see how the resource usage and the latency vary based on the number of bits we use to represent it. The takeaway is that we're still at less than 10% of the maximum latency. So the 4 microsecond limit would equate 800 clock cycles of this 5 nanosecond FPGA. Forgot to mention that the clock cycle is 5 nanoseconds here. And the resource usage is good. So for graphs with 28 nodes and 56 edges, the throughput optimized version is very feasible as a level 1 trigger. We do have to see in the future though if we can, scale this to larger graphs. Then there's a resource optimized implementation. We get to 450 clock cycles, which is 2.25 microseconds. So still below the latency, and resource usage is still not 100% for any of these different computer architecture components. So that's, it's a feasible implementation. And just to check, we varied the actual graph size to see how it affects the, the latency and the resource usage. We see that at about 448 nodes, 896 edges, we at less than 1,000 nodes, we start creeping up on this 4 microsecond limit. So for larger graphs, probably wouldn't be feasible as a level 1 trigger, but it could be feasible as a high level trigger or as like a CPU coprocessor application. But resource usage is still good. So it's a pretty high-end FPGA that we're targeting, but resource usage is all good. So summary and outlook for the throughput optimized backend scales to smaller graphs. It's feasible as a level 1 trigger because it's less than 1 microsecond. For the resource optimized implementation, scales to larger graphs. It can be used as an L1 trigger for smaller graphs or as an offline high level trigger for larger graphs or as a CPU coprocessor application. In the future, we need to increase the synthesizability of the throughput optimized backend so we can scale it to larger graphs. And for the we need a hardware FPGA implementation of the rest of the particle tracking pipeline, which is the mainly the preceding graph construction phase and the succeeding full track reconstruction phase. So yeah, it's so far it seems like a feasible project, but it needs a lot more work in the future. And thank you for listening.
Very interesting talk. Questions? There's the first one already.
Yeah, I think what you're doing is amazing. I have a question regarding the actual workflow, I would say, because when you're implementing stuff on an FPGA, you're extremely close to your hardware, as you said. And I feel a lot more comfortable talking about FPGAs than about neural networks. But what I understand is that you don't really know in the end how it's doing, what it's doing. So how would you then go to your next step and work with your FPGA and debug it and get it to work efficiently, perfectly?
Are you saying you don't know how the neural networks are doing what they're doing or how the FPGAs are doing?
No, I mean, what the FPGA is doing, you can just tell it to do, but yeah, the neural network is the crazy thing.
Yeah.
So how do you later go into your FPGA, look at your signals and say, oh, that's not supposed to happen. We have to change that. And you not even know what the neural network wants you to do.
Oh, yeah. Okay, I kind of get what you're saying. So, so when we were first developing the HLS for ML software that translate this software, we were developing this add-on, we would basically see the output of the Python neural network and we'd make a Python neural network. We'd hold that one, and we'd also create an HLS version of it, and we just compare the output of the two. And it's like there is artifacts of the quantization, so they don't agree exactly, but it's well over 99%. So we know that this FPGA neural network is doing the same exact logical steps as the Python neural network, but it is a lot of debugging code and stuff. But that's the good thing about this tool is we only need to do it once. You know, we've created like the template backend, and now it should work all the time for any graph neural network setup. Makes sense?
Yeah. Thanks.
I had a question about your. I'm Chris. Yeah, a question about your assumptions when you feed the data into the FPGA stuff. So do you assume that your entire detected data is going in on one clock cycle and you construct the graph, or do you wait, or do you have some sort of buffer time that the detected data has been read in and you can start your graph construction as that's been read in?
Yeah, no, that's a good question. So yeah, we can't just load all of the detector hits onto the FPGA at the same time, because there's no FPGAs with that high of a bandwidth. So we'd have to serialize them one step at a, like batches of detector hits at a time. But yeah, that's not like developed yet. That would be once we develop the full pipeline.
Okay, so your latency figures don't include that.
Yeah, no, this is just for once we have the neural network, like beginning to end, but it's not like reflective of like the full pipeline.
Okay, and then I guess the other side of that question is then what does your output look like? Are you outputting something per clock cycle and everything comes out on the same clock cycle at the end, or do you have an idea of your?
Yeah, so the latency, which is right, the time between input one and output one, that's what I've been basically talking about this whole time. But there's initiation interval, which is slightly different. It's the time between input one and input two. So we can feed input two before we have output one. And initiation interval hasn't been like a limiting factor so far. So far, it's been mostly latency that's been, the hard limit we have to reach here.
And it's a fixed latency for multiple different graphs, or?
Yeah, basically because it expects a graph of a fixed size, it has a fixed latency. But yeah, the 4 microsecond level 1 trigger latency limit, that's for the whole pipeline.
Yeah.
So we need to be below 4 microseconds.
There's another one before. I have a question about the truncation. What is the typical size of the graph that you have to truncate with a typical graph on TrackML? And what's the size that you have to remove from the graph?
Oh yeah.
You don't fear that will break your physics efficiency?
Yeah. Well, we did run some numbers on this. We found the effect for when we pad to 113 nodes and 196 edges, given the graph construction parameters that I mentioned earlier, like the phi slope and the Z0 max, we found this effect to be like less than 5%. But it is, we've quantized it 5%. I don't know if that's like acceptable.
Not all peaks have the same. I mean, if you
Oh yeah, on any specific graph. Yeah, on average it was 5%. Between 50 sample graphs that we tested from the TrackML data set. So again, the hope is that with a large enough FPGA, this effect will go away.
Okay.
Almost my question, but almost. Can you, during the graph building, learn which part is best to truncate?
I have
you don't unroll the tool edge classification there, but once you have it, it's trivial because it tells you which one you could truncate. But doing the graph building, could you kind of get a hint which part you can truncate without having a big loss?
Well, we do this. So we obviously do this based on some logical functions. And it was a bit of a challenge to even define for ourselves, what is the best nodes or edges to truncate? Like, should you get rid of like the least connected nodes first? And so I think if you can define that, and yeah, sure, you can train a model to do it. But we haven't really defined like a hard definition of, what's the best thing to truncate? Like, what's the
Well,
best way to
truth
go
should
about
tell
it?
you.
What?
The ground truth should tell you. The ground truth tells you a posteriori that you could have just ignored that part.
Oh, yeah. No, that's a good way of, that's a good way of thinking of it.
The most obvious way to truncate is truncate the edges. Nodes, you probably don't want to go the one way. Those are like space point.
Yeah, the problem is that the FPGA expects a fixed number of nodes and a fixed number of edges. So if we have to truncate nodes, we have to truncate nodes. We can't get around it by truncating edges. Although truncating edges would save us memory, the FPGA just isn't expecting, that number of edges and that number of nodes.
Okay. In the interest of time, I think we should move on. Let's thank the speaker again.
Thank you.